So let's start with a little nomenclature. Okay. All right, before we get started, there was a question in the chat, how many synthesis problems can we expect? Because chapter 11 is synthesis and synthetic strategies, and we're now doing synthetic strategies in every chapter. You know, I would expect 10 or so, 6 or so. So, you know, anywhere from 5 to 8. And, you know, there's also a question of how involved. You know, you're probably going to have some 2 steps. I mean, if you think about just a acetylide addition to a carbon, you know, that's already 2 steps. So, you know, you'll have a variation of 2, 3, 4 step synthesis type problems, maybe even up to the 5, 6, if some of those steps are multiple. So chapter 11 is synthesis. So we're going to have probably more synthetic strategy type problems on this one than we would have on previous exams. Okay, so let's take a look at the questions. I mean the nomenclature. So if we look here, we have 1, 2, 3, 4, 5. Okay, we could have also gone the other direction. 1, 2, 3, 4, 5. If we go in the blue direction, that actually gives me the yne as the lowest. Since I'm naming this as the yne, that's the way I want to go. So this is going to be pent-yne. I do need the 1. I can't assume where that yne is. And then the methyl gets 4. All right. So since we're naming it as the yne gets priority. So we go 1, 4 process. In the next one, we have again 5. Most of these are going to be 5. So 1, 2, 3, 4, 5. Going in this direction, 1, 2, 3, 4, 5. Right, this is going to be the alcohol is going to be the priority, and it's actually the only group here. So we have 2 pentanol. Okay, but stereochemistry is indicated, so we need to look at that. So let's put in our lowest priority. So we have 1, 2, 3, 4 is going back. So if we draw from 1 to 2 to 3, that's going in the counterclockwise direction. So that's S. So this is going to be S2 pentanol. Okay, questions about either of these? All right, the next one. Here we have hexanol. Right, we can put the 1 in, but it's not necessary. And then we have, naming it wrong already. 1, 2. So I'm going to have 2 hex all, cyclohexene. I'm messing up today. Cyclohexene all. So the 2 goes with the ene, the 1 goes with the all. So 2 cyclohexene all. You could have also done it one all, but again, the 1 here is assumed to be the 1 because it's cyclic and I'm naming it as the all. So the 1's not necessary. The ene goes to the cyclohexene. Okay. And again, you wouldn't see both of these as an option on the test. Yes, you could also have this one. On this, you probably wouldn't see this. Again, if we had lots of different substituents, you could end up with something like this. So, you know, I would say that the last one is kind of the OCD way of doing it. The first one is really the IUPAC name. So if we look at the last one, but good question, good question. So the last one here, we have 1, 2, 3, 4, 5, 6, 7. Okay, we could have also gone 1, 2, 3, 4, 5, 6, 7. Here, we're going to go with the blue because the alcohol is going to be the final name. So we're going to have heptine to all. In this case, I'm going to move the 2 towards the all, right? And then I'm going to move the 4 out here. I could also do the hyphens, but this would usually be reserved for something that has lots of different substituents. Okay. And so 4-heptene to all is going to be the preferred name. The hept4-ene all would be if you had a lot more substituents that made it more complex. Okay, so a little bit of nomenclature going to be on the test. So now let's look, a lot of it is going to be reactions and understanding reactions. There's going to be, you know, mechanistic style questions, but let's do some try this. This one is predict the products. So we'll do 3 of these at a time, give you about a minute to work on them. Okay, let's take some time on this one. On this one, I'm going to say monobromination. I could have also said this by adding 1 equivalent. Again, often what they'll do is they'll show the monobromination, or they'll have monochlorination. And yes, that's diisoamyl borane. And that's an MY. Yep. My timer. Okay, so that was about a minute. So if we look at the first one, because diisoamyl borane, right? We could have also had 9-BBN. Both of those are the same. Second step, so this is hydroboration oxidation with an alkyne, and the result on that is going to be the aldehyde, right? So we're oxidizing that up the aldehyde, and we have 1, 2, 3, 4, 5, 6 carbons. So 1, 2, 3, 4, 5, 6 carbons. Okay. Right. Second one, we're doing bromination. I said monobromination product is often in the problem. And if we look at the bromine with a tertiary hydrogen here, right, that the bromine is going to add there, and we're really not going to see any competition. So again, tertiary hydrogen, right, we have a 1600 ratio to 1 for a primary bromide, so we get a highly selective reaction with the bromine. And then the last one here, we have the SOCl2 with pyridine. This is going to be a substitution, SN2 style. No stereochemistry is shown, but so I don't have to show any stereochemistry. And we get the chlorinated product here. Okay. Questions about these three? Let's try another set. And again, you should have flashcards for all of these. Hopefully you've been working on those. Okay, let's take a minute to look at these. Again, this is much faster than what you'll have on the test, but it gives us a good chance to try a bunch of these and kind of bring up to memory what you should know. All right, so the first one, this is sodium in ammonia. It's not sodium amide, right? We're not talking about sodium positive and NH2 minus. So in this case, this is a dissolving metal reduction. And in a dissolving metal reduction, we end up with the trans. So 1, 2, 3, 4, 5. Right, so we end up with the trans alkene. Next one, we're doing an allylic or benzylic bromination with NBS and light, or NBS and heat. Either of those would have worked. And what this does is give me selectively, right, addition at the benzylic or allylic position. And the last one, this one, let's go ahead and work through the mechanisms since we haven't seen many mechanisms this morning. Remember, this is a hydride donor. So nucleophile attacks the electrophilic carbonyl, pi bond breaks. That's our leaving group. Have the O minus, H, and now we have the H added. And then we get protonation. We get a proton transfer here. So this goes there. So our product, I should go ahead and draw that right, is the alcohol. All right, questions about these three? Could we have used lithium aluminum hydride in that last one? Yes, for the aldehyde, either sodium borohydride or lithium aluminum hydride, followed by a proton source like water, will work, right? Remember, the big difference is that sodium borohydride can be in an alcohol. Lithium aluminum hydride, you follow it with a proton source, so it's a 1-2 reaction. Okay, let's shift gears a little bit. Let's select for some reagents, and then we'll move into some synthesis. Okay, let's take a little time. Think about these. Okay, let's take a look. Okay, in this first one, we are changing our carbons, right? So over here, we have 6 carbons. Right over here, we have 4 carbons. So we are adding 2 carbons to this. This is a terminal alkyne, so we can turn this into a acetylide by adding sodium amide. We need a good strong base. And then second, now we can add how many carbons we have, and we have 2 carbons. Should be primary, right? If it's secondary, there's a complication with elimination. So primaries are the ones that work best, and primaries favor the substitution and not the elimination. And so we get 2 carbons. So just ethyl bromide in the second step. Okay. Questions about this one? Okay, the next one here, we're going to the bromine, right? We're adding the bromine. It's important to notice that that is allylic. Right. Since we have a double bond here, could we have used Br2 and light? For this one, because of that alkene, this would give us complications because the bromine could add directly to the alkene, right? We've seen that reaction before. So what we want to use here is our NBS and light, right? And so remember, NBS is right. So NBS. Okay, questions about these? Okay. Again, you know, it's fine to flip through your notes and stuff and look for these right now. If you don't see them, highlight them. If you don't remember them, the thing to think about is you know, if you see something and you don't recognize it, that's something you spend a lot of time on. If you see something today and you do recognize it, that's something you can spend less time on. So let's do 2 more. Yeah, NBS adds allylic, so it adds benzylic and allylic, so it favors one away from a pi bond. All right, so one of the things you'll notice that I'm doing with this is I'm always asking myself what's going on. That's a good place to start, is look at this and see what's happening. If here, right, we're going from an ester to an alcohol, right? If you see any of these, one of the things that's problematic anytime you're working an exam or a problem is for your pencil to stop. This is something an old chemistry teacher in high school taught me, is, you know, always keep your pencil running. So if you see something you don't know what the answer is, don't stop and stare at it. Think about what you do know. I know that's an ester. I know that's an alcohol. I can also say that this looks like a reduction, right? I have more bonds to electronegative atoms here. I have less bonds to electronegative atoms here. Okay, so this process seems to be a reduction. Right. From there, right, then I can start thinking about my reducing agents. I could have hydrogen and, let's say, a metal like palladium on carbon. We could have sodium borohydride, right? So I can think about these as my reducing agents. I could have sodium in ammonia, right? I could lithium aluminum hydride followed by water, right? So what I'm trying to demonstrate here is just, you know, think about what all my reducing agents are. Have we seen hydrogen and palladium with the carbonyl? We have, but only with ketones and aldehydes, right? So not with an ester. Sodium borohydride and lithium, sodium borohydride and methanol or ethanol. Well, the sodium borohydride is too weak to react with the ester, right? Or the carboxylic acid. So we know, although it does react with carbonyls, it doesn't react with esters. Sodium and ammonia, well, that's the reducing agent we had for the alkyne. It's a specific reducing agent and doesn't work with most anything other than the, well, it will reduce chlorine, but all that does is make salt. So that's an alkyne. And so then lithium aluminum hydride. So our answer here is lithium aluminum hydride. It reacts with carbonyls like the sodium borohydride, but it's more reactive. That's why we have to separate the proton source. Okay, and so lithium hydride will reduce an ester all the way down to the primary alcohol. Okay. Questions about this, or questions about kind of the strategy if you see yourself stuck on a problem? Okay, keep your pencil moving. And again, I highly recommend having some scrap paper. Please do not have your notes, just a blank piece of scrap paper, and work through it. Okay, so here again, we're looking, not again, but here looking, we go from an alcohol, right, to an aldehyde. What's happening is an oxidation. And in this oxidation, then we look at the process. We're going from an alcohol to an aldehyde. I should finish the word aldehyde. So we're not going to carboxylic acid. Right? We're not going through carboxylic acid, so we have to stop at the aldehyde. So if we think about these, we have our chromic anhydride, right? We've got PCC and methylene chloride. We've got the Swarin, and we got the Des Martin, right? Of these, which of these will stop at the aldehyde? Well, these three would stop at the aldehyde. That one would not, right? That one would go all the way to the carboxylic acid. So since it's multiple choice, you're going to have one of these three, or all of the above. But if I'm just picking right now, if you put the PCC in methylene chloride, again, methylene chloride is not a reagent. It's signifying something. It's signifying that I'm using an anhydrous solvent. Okay. Questions about this one? Any three of these would have worked, right? I could have had the PCC and methylene chloride, the Swarren conditions, or the Desmart reagent, DMP. All right. Okay, let's try a couple more. And again, we'll give you a little more time. I find these students have a little bit more problem with selecting the reagents than actually giving the products. So that's why we're doing 2 at a time now instead of 3 at a time. So let's take a look. Okay, so we start with an alkyne. All right, we're going to an alkene. And this is a cis alkene. This is a reduction. All right, so it could be hydrogen and palladium on carbon, could be hydrogen and Lindlar's catalyst, and it could be sodium and ammonia, right? So those are my 3 reagents with an alkyne. The hydrogen and palladium, that would have given us an alkane, right? The Lindlar's catalyst, that works. How about the sodium and ammonia? That would have given us the trans alkene. Right? So that's not going to work. So it's going to be hydrogen and Lindlar's catalyst. And the next step, we're going from an alcohol to an alkene. Right, we have 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6 carbons. So we're not changing our carbon skeleton. So really, it looks like what we need here is an elimination. But as a primary alcohol, would sulfuric acid and an E1 type elimination work well? Now, an E1 wouldn't really work well. So if we just threw in concentrated sulfuric acid in this, this is going to take a whole lot of energy and create a lot of messy side products. So the best way to do this one would be to turn that alcohol into a good leaving group with the tosyl chloride. And then here we can use any base we want, right? But we can just use something simple like the ethoxide to get us our product, right? So what we're doing in this case is an elimination. And since this is primary, I want to focus on E2 style E2 style eliminations. All right, questions about this one? Okay, let's change gears a little bit and then we'll get into a couple of synthesis problems. Okay, and on these two, I want you to rank. Right. So the first one, give me the most acidic. Now this next one, give me the most stable. And to make it a little easier, 1, 2, 3, 4. Okay. So let's take a little time on this one. All right, so if we look at the most acidic, right, if we're looking at these, what you should consider is, like, what is the conjugate base? So I would go ahead and draw this. So we got the oxygen negative. And so we got the oxygen negative. So nitrogen negative sp carbon, right? sp3 carbon. So if we think about the sp3s, these are sp3, this is sp3, right? Those are pretty easy. The oxygen is going to be more stable than nitrogen. Nitrogen is going to be more stable than the carbon, right? But then over here, right, we've got a sp. What's going to happen with the sp? So we know that the sp, right, is going to be more stable than the nitrogen sp3, right? So when we look at our answer here, we're going to have 2, which is my OH here, right, is going to be more acidic than 1, which is going to be more acidic than 4, which is my nitrogen, which is going to be more acidic than the sp3 term. Okay. Questions about this one? Remember that we use 4 to deprotonate 1. That's how you can keep that one straight, is that 4, the amide, the nitrogen, deprotonates the 1. Right, so this type of species deprotonates this type of species. That's why we know the order of those two. The next one we have are tertiary radicals, secondary radical, tertiary stabilized. Why is it stabilized? Because it's allylic. I don't know why I can't spell that word. So it's allylic and then primary. Okay. So most stable is going to be the stabilized tertiary, right? Then the tertiary, then the secondary, and then the primary, right? The stability of radicals follows the same trend as carbocations. They're both electron deficient species, and so therefore they have similar stabilities. Questions about either of these? So we're going to have some acid-base type questions, right? That's possible because of the pKa difference to create the acetylide, and then we've got radicals in chapter 10, so need to be thinking about radical stability on that. So let's do some retrosynthesis. And I'm going to do these one at a time to give you plenty of time to work on these. And I'm going to extend this out a little bit. I'm going to give you 2 minutes on this because it is somewhat involved. Okay, so let's try this one. Start with your carbons, right? Then start thinking about your functional groups. Okay, let's take a look. So on this one, first let's analyze, right, our carbon structure. So over here I have 6 carbons. Over here I have 6 carbons. But my structure here is acyclic, right? And over here it's cyclic. So I know I'm going to be doing some type of carbon skeleton change. I'm just not going to be potentially adding carbons. I don't need to add carbons. So if we think about what could break a carbon-carbon bond, right, there's only a few things that could break a carbon-carbon bond. And right now we really only know of ozonolysis, right? So we're probably going to have to use ozonolysis here, and ozonolysis occurs with alkenes, right, or alkynes. For a 6-membered ring like this, we're not going to get an alkyne in that ring, so we're probably looking at an alkene. So that would allow us to break open that ring, right? So when we get the ozonolysis of the ring, right? So what I need to do is get this to that, right? And then I need to get that to 1, 2, 3, 4, 5, 6. This, right? And then I need to get this to that, right? So break it down in its steps before you start worrying about the reagents. Now, over here, I don't even have a leaving group. So the first thing I'm going to need to do is going to be creating something that I can eliminate to get the double bond. So for my first step, it's going to be, and let's change colors a little bit. So my first step, I'm going to take my hexane, and add a halide by doing a radical reaction. That's more or less the only reaction you know for alkenes, and it's really one of the only reactions besides burning it for an alkane. So here, if we take that, we get the bromide, then we can do the elimination, right? Here, any good base will work. I'm going to use the methoxide. That will give me my double bond. And then if I do my ozone, right, so ozone followed by the sodium hydrosulfite, right, or hydrogen sulfite, that gives me my acyclic. So that's cleaved open. Now I have my carbon skeleton change. And then if we look at our carbon skeleton change, now I've got the dialdehyde. All I have to do is get to the dialcohol. So I can use my sodium borohydride and methanol. I could have also used lithium aluminum hydride followed by water. And that will give me my diol. Okay. Questions about this synthesis? We did have a carbon skeleton change here. It was going from a cyclic to an acyclic. There's only a few ways to do there. So whenever you have one of these, it's directing you in a certain direction, right? So when you have a limited way to get from one place to another, it is trying to help you focus on that. Okay. All right, let's try another one. And this one's a little bit more straightforward, so I'm gonna just give you a minute on this one. Yes, you could have used ozone and DMS, right? So you just need a reducing agent in that second step. For this one, we have 4 carbons, right? 4 carbons. The localization, right? We have 1, 2, we have 1. So it looks like carbon skeleton, we're good. Really what we need to do is figure out how to go from an alkene to an aldehyde. And we need to focus regiochemistry here on the least substituted position. So therefore, on this one, we're going to take the double bond. We're going to do BH3 THF followed by hydrogen peroxide and base. That will give us our regiochemistry, right? That one position. And then what we need to do is oxidize that. And we have 3 ways to oxidize that. I'm going to go ahead and show, the DMSO, COCL2, followed by triethylamine. give us the aldehyde. So synthesis problem, but pretty straightforward on this one. Let's do one more, and then I think we'll be out of time. Let's go ahead and look at this one since we're running short on time. We are changing from 4 carbons to 7 carbons. We start with an aldehyde. And we end up with a ketone. If we look at where this is, it looks like what we're doing is adding the carbons. Now remember, we can do a Grignard to add the carbons, and then we could oxidize it back up. Right, so we haven't shown Grignards today, but don't forget about them. Right, so if we take our aldehyde, react that with our 3-carbon Grignard. Right, first step, second step, water. We're going to end up with our correct carbon structure, right, with the alcohol. So this is a preparation of alcohols. Grignards react with aldehydes and ketones well. They also react with esters. Okay, and then all we need to do now is do the oxidation. And here we could use any oxidation we want, right? So the chromium acid, chromium anhydride, we could use the disodium chromate, we could use the PCC, we could have used Sworn oxidation, could have used Des Martin, right? All of those work because we're going from a secondary alcohol to a ketone, okay? Right, so don't forget about your Grignards, okay? Didn't do any early practice on that one. So here's your Grignard note, put an asterisk. Grignards are very helpful in changing carbon structures. Okay, that's